In this last lecture on the subject of kinematics, we will go over numerical examples of projectile motion. This first problem involves a bomb that is released from a plane that is traveling horizontally eastward. It starts above the ground at an altitude of hi. The trajectory of the bomb will look like this. We want the target to be where the bomb hits the ground. We will use the same reference directions as discussed in the previous lecture. The givens are the initial speed, the angle that the initial velocity makes with the horizontal, and the initial height of the bomb. We are looking for the horizontal component of the displacement, which is given through this equation. Since in this example the initial velocity is horizontal and cos of 0 is 1, this equation can be simplified to this. We need to express delta t in terms of our givens. We will use the requirement that the vertical component of the displacement must match the drop in height. The negative sign in front of hi is due to our choice of vertical reference direction. What follows is the expression for the vertical component of the displacement as a function of delta t. This equation can be simplified by using the fact that theta is 0 and sine of 0 is 0. There was no vertical component to the velocity initially. Isolating for delta t gives this, mathematically, but physically we are only keeping the time duration value that is positive, since the final time needs to be later than the initial time. Substituting this expression for delta t in the equation for delta dx gives this. All that is left now is to substitute the numerical values for the givens in the equation. Please note that the ratio 1000 over 3600 is necessary in order to convert kilometers per hour to meters per second. Since g is known in meters per second square, it is customary to convert all other measurement unit of length to meters and the measurement unit of time to second to be able to use g equal to 9.8 meters per second square. The final answer is 7.10 times 10 to the 2 meter. In writing this answer, we are viewing g as a constant and do not consider it to be relevant for the decision about significant digits. This second example is similar to the first one, except for the fact that the initial velocity of the projectile is not horizontal. The ball is thrown from the top of a cliff with a height hi. The initial velocity is a vector with a positive vertical component. Here is its trajectory. We will choose this set of reference direction, and these are our givens. As before, the horizontal component of the displacement is given by this equation. We will not simplify it by using the value of theta at this stage. The requirement for the vertical component of the displacement to involve the drop in height is stated the same way as before, except that we cannot conveniently get rid of the term vi sine theta delta t as before. Isolating for delta t is a bit more difficult and requires you to notice that we are dealing with a quadratic. This last equation can be rewritten this way. You can solve this equation by using the quadratic formula. I am assuming that you're familiar with this concept at this stage from a previous course in mathematics. The quadratic formula is usually expressed as minus b plus and minus square root of b squared minus 4ac, everything over 2a. In this case, a is g over 2, b is minus vi sine theta, and c is minus hi. Here is what you get after using the quadratic formula. As in example number 1, we will only keep the solution where delta t is positive. And after some simplification, we can write delta t like this. Note in passing that if theta was 0, this equation would reduce to the same equation we had for delta t in example number 1. Now using this expression for delta t in the equation for delta dx, we get this. Substituting the numerical values gives this. Then using a calculator leads to a numerical answer of 9.31 meters. This third numerical example uses the same setup as example number 2, but the question is about finding numerical information about the final velocity, that is the velocity when the ball hits the ground. So let us copy again the drawing and the list of givens from example number 2. We will add the final velocity to our drawing and define alpha as the variable name for the angle at which the ball hits the ground at the end of the time interval. The horizontal component to the final velocity is given by this equation. For the vertical component of the final velocity, we will use this kinematic equation. Using the fact that delta dy is minus hi gives this. Isolating for Vfy leads to two values, but we will only keep the negative value because here the final velocity should have a negative vertical component. We are now in a position to evaluate the final speed, having expressions for its components. To simplify this expression, we might notice that the first two terms under the square root add to the square of the initial speed. Having established the equation that leads to the final speed, we are now able to use the values of our givens, and with a calculator evaluate the numerical value for the final speed. Now on to the task of evaluating the angle. If you form a right-angled triangle around the arrow for the final velocity, you can express the tangent alpha in terms of the components of the final velocity. Inserting the expressions derived in the previous slide for the components gives this. Isolating for the angle alpha leads to this expression. The next step is to substitute the givens and use the calculator to get the final numerical value. In summary, the ball hits the ground at a speed of 31.4 meters per second at an angle of 84.9 degrees below the horizontal. This final numerical example involves motion over a flat terrain and looks like this. We are given the maximum height and the range. We are interested in evaluating the initial velocity that leads to such a trajectory. The givens are the range and the maximum height. We will work with the time interval where the initial time is at the firing and the final time is when the shell reaches its maximum height. For this time interval, the horizontal component of the displacement is half the range. The vertical component of the displacement is the maximum height, and the vertical component of the velocity is 0, since it is the location where the shell stops rising and would next be falling. For the solution, let us start with this kinematic equation. Using the characteristics of our chosen time interval, this equation simplifies to this. We can then isolate for the vertical component of the initial velocity. Here, only the positive value for the vertical component was kept, since the shell must rise at the start. Next, let us use another kinematic equation that involves delta t this time. For our chosen interval, we can write this from it and isolate for delta t. Finally, let us use a kinematic equation that will use the horizontal component of the displacement. Substituting what we know about our special time interval gives this. We can now isolate for the horizontal component of the initial velocity. At this stage in our solution, we have expressions for both components of the initial velocity in terms of the givens. All that is left is to convert this vector in terms of magnitude and direction. The muzzle speed which is the initial speed, is the square root of the sum of the square of its component. Substituting the expressions for the components in terms of the givens gives this. Now we supply the numerical values for the givens, making sure that kilometers are converted to meters. And we use a calculator to get the numerical answer. The tangent of the angle that the initial velocity makes with the horizontal is related to the ratio of the components. The expressions in terms of the givens are again used, and after simplification we get this. Note that theta does not depend on the value of g. Isolating for theta gives this, and substituting the numerical values gives this. Since this equation does not involve g, there is no need to convert kilometers to meters, as long as h max and r are using the same measurement units. The use of a calculator leads to this answer. All that is left is to summarize our final answer. And with this, we end the first unit of this course of Physics 11. This unit was about describing the motion of an object quantitatively. Next, we need to look at other physical quantities that will be useful in order to predict why an object has a particular motion. It involves the concept of forces. This will be the subject of the next unit as well as the next installment.